In our last example for the ratio test, we're asked to use the ratio test to assess the absolute convergence or divergence for the series the sum equals 1 to infinity of 1 over n. So we begin by looking at the absolute value of a sub n plus 1 over a sub n, where a sub n equals 1 over n. That is, we have the absolute value of 1 over n plus 1 times the reciprocal of a sub n is an n over 1, or simply n divided by n plus 1. When we take the limit as n goes to infinity of n divided by n plus 1, we know that this will equal 1. We can prove it by dividing each of the terms by n. So, since this equals 1, we cannot conclude anything from the ratio test. Instead, all we can do is state that the ratio test is inconclusive. Because it gave us the circumstance where our limit was equal to 1. Now, for this particular function, we can actually conclude that it diverges because it is a p-series with p equal to 1. If you remember, that was our harmonic series, is what we called it. But even though it diverged here, the ratio test was not able to tell us that. We had to turn to another test. It's possible that we could have had a series that converged. Notice if we had instead the sum from n equals 1 to infinity of negative 1 to the n over n, we would have the same ratio when we looked at the absolute value of a sub n plus 1 over a sub n. We would still get the n over n plus 1 because the absolute values take away that negative 1 to the n. And we knew that this converged by the alternating series test. So again, the ratio test is inconclusive with the example we had, but it is very possible to have either circumstance where the ratio test is inconclusive but our series diverges, or the ratio test is inconclusive and the series converges.